In this video, we're going to talk about consistent and inconsistent systems. So let's begin with a definition. So a linear system that has at least one solution is called consistent. So if a system has a solution, at least one, it's consistent. But if there are no solutions, we say that it is inconsistent. Okay, so how do we determine if a system of equations has a solution or not? It all boils down to looking at the RREF, the reduced row echelon form, and seeing what appears. And in general, there's three scenarios. There's three possibilities for what's going to happen with our augmented matrix. So the first scenario is, I'll talk about how we could have no solution. We'd have no solution if we have a row that looks like, a bunch of zeros, augmented bar, and then a non-zero thing on the other side. And I'll explain why with an example. But another way to describe this a little bit more succinctly is I say that the last column is a pivot. Okay. So I'm going to put this double-sided arrow, and the double-sided arrow means if and only if. If and only if. So the last column is a pivot if and only if there is no solution. So no solution, and that is when it's inconsistent. No solution means our system is inconsistent. So let's look at an example to see why that's the case. So let's suppose that I had the matrix 1, 0, 7, negative 12. Let me write down the other rows more quickly. Okay, so just to do it more quickly, I've made the other rows just appear. Okay, so when I write down the equation for each of these rows, what I get is for the first row, I'll have x1, there's no x2 term, so I'll leave space, plus 7x3, that equals negative 12. For the second row, the equation I have is x3 equals 7. And then for the last row, I would have 0 equals 5. But 0 equals 5, that's impossible. That can't happen. So because of that, there is no solution. No solution. So notice that what tipped me off that there's no solution is when there's a row of all zeros and there's something that's not 0 on the other side. Because that'll give me an equation that looks like 0 equals something that's not 0, like 5. Okay, so what does it look like when there is a solution? So when there is a solution, then, the last column is not a pivot. So that means we won't have a row of all zeros and then something that's not 0 on the other side. So if the last column is not a pivot, there's sort of two other sub cases within that. So one is, what if there are no free variables? So I'll consider the case where there's no free variables, and I'll consider the case where there are free variables, because they're slightly different. So in this situation, there is a unique solution. So unique solution means that there is exactly one. So let's look at an example to see why. Okay, so this time I'll do 1, negative 1, augmented with 4, and I'll do 0, 5, augmented with 15. Okay, so first off, is this an echelon form or reduced echelon form? Pause the video for about 30 seconds and think about that. So 4, 3, 2, 1, pause the video. Okay, so is this echelon or reduced echelon form? Hopefully you guys pause the video. If not, go ahead and do that now and think about it. So I'm going to go ahead and start to talk about it. So this is in echelon form, not reduced. There's two reasons why. So this 5 is a pivot, as is the 1. And the pivots all have to be 1 to be in reduced form, and they're not. Another reason why it's not in reduced form is the number above, both below and above all the pivots have to be 0. And that's not happening with this negative 1 here. So this is just echelon form. So when something is in echelon form, at this point we can go ahead and convert it to equations if we want to. So the equation for the first row is x1 minus x2 equals 4, for the second row is 5x2 equals 15. And the second equation is really easy to solve. From the second equation, I'll get that x2 equals 3. And if I know what x2 is, I can just plug it back in to get x1. And that's easy enough. So I get x1 equals 7. So x2 equals 3 and x1 equals 7. That's my solution. So notice that there's only one. There's only one solution because it's an ordered pair. There's two variables and only one possible solution here. So if we convert, once we have our matrix in echelon form, if we then rewrite them as equations and solve, this will require back substitution. So for example, notice that after I got x2, I had to then substitute that back into the other equation to get what x1 is. So I'm going to call this, what we just did here, I'll call this method 1. So in method 1, we're using the echelon form. But what would happen if we instead had to use the reduced echelon form? So method 2, let's use the RREF. So let's row reduce this. So if we row reduce our matrix, well, let's divide the second row by 5. So the first row stays the same. If I divide the second row by 5, I'll get 0, 1, 3. Okay, so we have divided row 2 by 5 and inserted that into row 2. Okay, so now to get this in reduced form, there's one last thing I got to do. So I know what the pivots are. They're this one and this one. So I have to make all the numbers above the pivots a 0 to finish it off and put it into reduced form. So I would have to add row 1 to row 2 and insert that into row 1. So doing that gives me 1, 0 augmented with 7, and the second row is the same, 0, 1 augmented with 3. And the advantage of this is now when I convert these two equations, the first row is x1 equals 7, the second row is x2 equals 3, so I got the same answer that I had before, but the advantage of this is I don't have to back substitute. So that's the trade-off there. If you put something in echelon form, that will require less steps in terms of row operations, but then you may have to back substitute once you convert to equations, and that might end up being more. If you put something into reduced form first, it might be a little bit more tedious to get your matrix all the way down to that form, but you guys are going to get so much practice at it that you'll be pros and great at this. But the advantage to doing that is once it's in reduced form, after you convert it to equations, you don't have to back substitute. So there's one more scenario for what our augmented matrix could look like, and that's if the last column is not a pivot, just like in the second case, and there are free variables. So when that happens if and only if there are, it turns out, infinitely many solutions. And we've actually seen an example of this already in the last video, so I'm going to go ahead and just paste that here for us to see. So let's remind ourselves, we did this example in the last video where when we row reduced it and put it into reduced row echelon form, the last column didn't have a pivot. So that's what told us the system was consistent. So this is going to be consistent. And if I forgot to write this earlier, but case 2 was also consistent. Let me go ahead and write that first and then return back to this. Okay, so here's case 2. Let's also go ahead and write down that this is also going to be consistent. Remember, a system is consistent. That means it has at least a solution. So in case 2, there was exactly one solution. So that's definitely consistent. In case 3, there were infinitely many solutions. So there's definitely at least one. That's why it's consistent. Okay, and the reason why there are infinitely many solutions is because, so the fact that the last column is not a pivot means I don't have just a row of all zeros on the left-hand side of the augmented bar. and something non-zero on the right. So because I don't have that, there is a solution. The reason why there's infinitely many is because there are free variables here. And the fact that they're free variables means that, I can let these variables be whatever I want, and that gives me a bunch of possibilities. Like, for example, if x2 equaled 0, let's just keep it simple, x2 equals 0 and x4 equals 0, we would get that x1 equaled negative 9, x2 equals 0, x3 equals 4, x4 equals 0, and x5 equals 3. So that is one possible solution. But by changing what x2 and x4 are, I would get an infinite number of solutions here.